Welcome to the chemistry universe. Welcome to the wonderful world of NCERT discussion. And in this episode, we are talking about states of matter. Essentially, we're talking about gases, but yes, it is titled as Unit 5 of NCERT 11th, which is states of matter. This is Shishir Mittal from Vyas Certification. Be with us. Well, the question says, what will be the minimum pressure required to compress 500 decimeter cube of air at 1 bar to 200 decimeter cube at 30 degrees Celsius? Now, what is to be done? What is the standard way of solving such problems? You know, the best and the most beautiful way is when you are reading a problem, note down the data which is given. So, first write down given. What is given? What will be the minimum pressure required? This is asked to compress, okay. Now, what we have V initial as 500 decimeter cube, and I hope you recall 1 decimeter cube is equal to 1 liter. So, this is essentially 500 liters of gas, of air. This is air at pressure is 1 bar and temperature is 30 degrees Celsius, and I hope you remember that when we are using any chemistry equation, degrees Celsius is absolutely useless. So, we would need to convert that to Kelvin. But again, I am just noting down what is given. Initial pressure, temperature and volume is given. Now, at 300 degrees Celsius, what is this? This looks like temperature. There are two meanings which could be attached. They have not given it as constant. To this much or to this much at 30. There are two meanings. The way the grammar has been framed, it's not very great, because initially, I'm very clear, initially it is 500 decimeter cube. Initially it is at 1 bar, fine. And final volume is 200 decimeter cube, that also is final. The meaning of temperature could be that final temperature is 30 degrees Celsius. That is one possibility. And it might also mean that all this drama is happening at 30 degrees Celsius. It is a double meaning question. Not good. But I mean, that is the way NCERT is. Now, if I just assume that final temperature is 30 and initial is unknown, unfortunately, this problem cannot be solved. Okay. So, we have to just become shameless and assume that temperature is constant at 30 degrees Celsius. Okay, fine. And what is this concept of minimum pressure? So, whenever you note this data, now you have to imagine a few things. Just imagine that initially the gas is enclosed in a cylinder, right? And then what do? You try to compress this gas. Now, when you compress this gas, when you apply pressure, the piston is pushed down. And say now the piston moves down to this location. So, it means that you have to apply a certain pressure. Now, initially, pressure is 1 bar. I have been given that initially pressure is 1 bar. So, when you are compressing, it is very obvious that if you are pressing something, the outer pressure has to be more. So, that means P external should be more than 1 bar, right? Then only you are compressing it. Fine. How much more? 1 bar, I mean, is it 10 bar, 100 bar, 1000 bar, million, trillion, quadrillion bar? It could be, I mean, if you use the pressure of entire universe, well, you can flatten it, no doubt. So, there is no limit to maximum pressure you can apply. But they are asking you minimum pressure. Maximum, there is no limit. That is why it is pointless. But there is some minimum pressure you might need to apply. Why? Because as you apply some pressure and the gas gets compressed, the pressure of gas inside is also going to increase. So, say for example, this volume becomes half. Temperature is constant. If the volume becomes half, pressure would become double. Initially, it was 1 bar. Now, if the volume is half, the pressure would become 2 bar. And you are still trying to compress it. because half of 500 is 250 and I'm supposed to still compress it till it comes to 200 decimeter cube, right? So do you see that the pressure outside also, if it is just more than 1 bar, that is not sufficient. It has to be at least so large that finally, till final volume of 200 decimeter cube, there is some final pressure, right? And you should be able to compress it till that pressure. Agree? You should be able to compress it till that final pressure. That means P external finally should be at least a little more than P final inside. Inside, whatever is pressure, you are compressing it. So outside pressure has to be more. Minimum, it has to be equal, but it can't be less. Otherwise, the piston will move up and it will start expanding instead of contracting, right? Fine. So what I understand by this minimum pressure is that this minimum pressure is nothing but at least the final pressure which is going to be there. And once we are clear with this idea, temperature is constant, so we apply Boyle's law. We have to find P minimum, or this is external. This is what is given and asked, but we have discussed and we have understood also a little part of what we need to do, and now we will execute that idea. How shall we do it? We will say at constant temperature, P1 V1 is equal to P2 V2, we apply Boyle's law. So P final is equal to V final, P initial, V initial. Now what was initial pressure? 1 bar. Initial volume is 500 decimeter cube. Final volume is 200 decimeter cube. This is P final, which if you cancel, it comes out to be 2.5 bar. So finally the pressure inside the vessel would be 2.5 bar. That means from outside also you must apply at least 2.5 bar so that you are able to push it till the internal pressure also increases to 2.5 bar. 2.5 bar, my dear, is the final answer. As we read, first we must write down given. And as we read the problem by small parts, we should keep on noting down the given data, like a vessel of 120 ml capacity. Now I have a vessel, so let me take a vessel. And its volume is 120 ml capacity, contains a certain amount of gas at 35 degrees Celsius. And pressure is 1.2 bar pressure. Perfect. The gas is transferred to another vessel. Oh my God. That means this gas is now being transferred to another vessel. Fine. Of volume 180 ml. No, this is a bigger vessel seemingly. Well, let me at least make it look bigger. Now, V final is 180 ml. This is initial. At 35 degrees Celsius, temperature finally is also 35 degrees Celsius. And please note, although for using this temperature, we should have converted this to Kelvin. But since temperature is not changing, we don't care. What would be its pressure? Oh my God. Given and asked. Everything has been diagrammatically conveyed. Since temperature is constant, dears, we don't need this. So we can simply apply at constant temperature for a given amount of gas, there is something called as Boyle's law. P1 V1 is equal to P2 V2, right? How much is P1? Pressure initially was, just remember, 1.2 bar. So we have 1.2 bar. Please substitute with units into 120 ml is 180 ml into P final. ml cancels. So P final is 1.2 into 120 upon 180 bar. This is 2/3. This is 0.8 bar. So final pressure would be 0.8 bar, and that's all. Using the gas equation PV is equal to nRT, show that at a given temperature, density of a gas is proportional to the gas pressure P. So how do we start? We start with equation of state PV is equal to nRT. So we just write down, given is PV is nRT, lovely. And then, well, we have a small formula, number of moles. Number of moles is mass by molar mass. Mass is small m, molar mass is capital M. There is a formula for number of moles. Can I write this? Yes. This is m by capital M RT. This is the reason, right? Now I could say Pm is m upon V RT. This is capital M, this is small m. Don't confuse, right? Mass by volume is density. So Pm is rho RT, where rho is density, which is mass by volume. Oh wow, it's done. Yes, it's done. I was supposed to show that density of gas is proportional to gas pressure P. So density is equal to P into M by RT. This is proportional to P. So density rho is proportional to pressure P. If you don't like the letter rho, instead of rho, you could write D. Rho. This is how it is pronounced, rho. Sometimes people like to use the small d as a density term. You can use that also. Hence proved. At 0 degrees Celsius, the density of a certain oxide of a gas at 2 bar is same as that of dinitrogen at 5 bar. What is this? I must write down the given data. So, given. At 0 degrees Celsius, density of a certain oxide of a gas at 2 bar is density of oxide of gas at 2 bar is same as density of nitrogen at 5 bar. This is given. What is the molecular mass of the oxide? How unfortunate. How do we solve this? This looks, well, a little different, but then we know one equation. And what is that? We know that Pm is equal to rho RT. Pm is equal to rho RT. That means density rho is Pm upon RT, right? Now density of oxide is equal to density of nitrogen. This is density of oxide at 2 bar, which is equal to density of nitrogen at 5 bar, right? So could I say that once I have this equation, if I write this for nitrogen, this whole thing is for nitrogen. If I write density of oxide of a gas, this is Pm upon RT for oxide of a gas. I could write it twice like this, 1 and 2. Can I divide them? Nobody can stop me. If I divide, what do I get? I get density of nitrogen, density of oxide of a gas. This is equal to Pm upon RT of nitrogen divided by Pm upon RT of oxide of a gas. Now, do I know anything about them? I know about their pressures, 2 and 5 bar. Now, I must substitute. So, this is pressure of nitrogen is 5 bar. Pressure of oxide of gas is 2 bar. That much I know. R is molar gas constant. It is constant, it cancels. molar mass of nitrogen. Do I know molar mass of nitrogen? Yes. Molar mass of nitrogen is 28 grams per mole. And molar mass of oxide we are supposed to find. What about temperature? Now, temperature at 0 degrees Celsius, this is the way it has been given. The student may be confused that it could mean that 0 degrees Celsius is density of a certain oxide of gas. It does not mention clearly whether it is applicable to nitrogen also or not. But since no other data is given, we have to assume that. And also, it is not very bad also. At 0 degrees Celsius. Now, they have stated initially and then they have went on with entire problem. So, it also could reasonably well mean that 0 degrees Celsius is a constant temperature that applies to the complete problem. So, unless they had changed the temperature here, I could assume that it is same. If it is same, temperature also will cancel. This is what I have. Density is same. So, this also cancels. This is 1 by 1. Why? Same. They have told it is same. So, what do I get? This is equal to this. I just solve 28 into 5 by 2. So, molar mass of oxide is 28 grams per mole into 5 bar by 2 bar. Bars get cancelled. 14 5s are 70. Don't eat away the unit. It means molar mass of the oxide of the gas is 70 grams per mole. Pressure of 1 gram of an ideal gas. Let me note down what is given. Pressure of, now mass is 1 gram. Ideal gas is given. Temperature is 27 degrees Celsius. Is found to be 2 bar. Now pressure is 2 bar. Very good. When another 2 grams of an ideal gas B is introduced in the same flask. Now my dears, let me tell you, when you're solving such questions, it is always very useful to make good sketches. I mean, just enclose this in a box. This is an ideal gas, this is in a box, right? This is scene 1. Now the moment scene changes, you have made a change. Draw the diagram again. Now you are having gas A plus gas B now, right? Same temperature, the pressure becomes 3 bar. Now temperature is same. I'm given temperature is 27 degrees Celsius. Pressure finally is now 3 bar. Find a relationship between their molecular masses. Well, mass of B is 2 grams. This is mass of A. Initially there was only gas A, right? So gas A. 1 gram of A was there. You introduced 2 grams of B and all this drama ensued. How do we solve this problem? First of all, it is very easy to get confused in such questions because, you know, students keep on juggling between when there is only one gas and when there is a mixture. The first step of successfully solving such questions is clearly demarcate them. This is scene 1. You had only gas A, 1 gram, temperature is 27 degrees Celsius, pressure is 2 bar. Now you have gas A plus gas B. Box is same, that means volume is same. Now, interestingly, volume is same and temperature also is same. Now, volume and temperature are same. Fine. So, the difference lies in number of moles and in pressure. Now, if you remember Dalton's law of partial pressure, what does it say? If you have same volume and same temperature, right, then total pressure. Now, this total pressure is nothing but partial pressure of A plus partial pressure of B. What is partial pressure of A? Whatever is the pressure exerted only by gas A when B is not there, that is partial pressure of A. And what is partial pressure of B? The pressure exerted only by gas B when A molecules are not there, that is partial pressure of B. Fine. This is total 3 bar pressure, right? This is A and B combined, okay? Do I know the pressure exerted only by gas A when gas B is not there? Yes, initially gas B was not there. There was only gas A. And what is that? That is 2 bar. So this 2 bar is nothing but partial pressure of A. So this is partial pressure of A, yes. Plus partial pressure of B. Therefore, I can solve partial pressure of B is 3 minus 2 is equal to 1 bar. Wow. There we are. Now I know that partial pressure of B is 1 bar. And with this data, let me write down PV is equal to nRT. PV is equal to nRT, right? And instead of N, I could write N is M by molar mass. So I can say that for gas A, it is V and T are constant, mass of A, molar mass of A. For gas B, it is PB into V, mass of B by molar mass of B, RT. Can I divide them? Nobody can stop me. And if I divide them, R cancels, T cancels, V cancels. Wow, what do I get? I get a simple, beautiful equation. I get partial pressure of A divided by partial pressure of B is equal to mass of A divided by mass of B into molar mass of A divided by molar mass of B. This was in denominator, it comes there. This goes up, yeah. Right? Am I given partial pressure of A? Yes, I know partial pressure of A is 2 bar. Sorry, this is B. Partial pressure of B is 1 bar. I made a silly mistake here. It is B here. B, please note. Mass of A was 1 grams. Mass of B was 2 grams. Molar mass of B and molar mass of A, I don't know. Nothing has been mentioned. Can I find the ratio? Yes, I can. Therefore, molar mass of A upon molar mass of B is 1 upon 4. So the ratio is 1:4. Find a relationship between their molecular masses. This or this, same they are. This is the relationship. 4 times molar mass of A is equal to molar mass of B. That is the way we solve it. The drain cleaner DrainX contains small bits of aluminium which react with caustic soda to produce dihydrogen. Now they are talking about DrainX, they are talking about caustic soda, hydrogen, aluminium. All that may look scary, but actually this has nothing to do with our problem. Let's read ahead. What volume of dihydrogen at 20 degrees Celsius and 1 bar will be released when 0.15 grams of aluminium reacts? Oh my God. Now they are reacting aluminium with NaOH, caustic soda, and they want the release of dihydrogen gas. They want to do calculations. This is gaseous state combined with mole concept. Unfortunately, you have to be aware of the equation. The first problem which you might encounter is that you don't even know which equation you have to write down. So let me write down the equation for you. If you do not know this equation, although this equation comes from inorganic chemistry, it has no relation with gaseous state or states of matter, you will be stuck in this question of state of matter. So they should have given the equation ideally. They haven't, because NCERT being NCERT, they can do anything. So let me give the equation to you. It is NaOH plus aluminium plus H2O gives NaAlO2, sodium metaluminate. Very beautiful equation. Sodium hydroxide can dissolve aluminium, and this gives you 1.5 moles of hydrogen gas. Wow. This is the equation? Yes. And what data has been offered to us? I am given temperature is 20 degrees Celsius. That is fine. And 1 bar, pressure is 1 bar, which is also superb. And I have 0.15 grams of aluminium. Reacts. NaOH has not been given. Caustic soda is NaOH. Since nothing has been given, I assume that I have enough H2O and I have enough NaOH. How many moles of hydrogen I'll get? Now, using stoichiometry, I can calculate moles. But I'm given grams, and atomic mass of aluminium is 27. So this is 0.15 upon 27 moles. Since atomic mass of aluminium is 27, I have so many moles of aluminium. And if I have so many moles of aluminium, now 1 mole of aluminium gives me 1.5 or 3/2 moles of hydrogen. How many moles of hydrogen will be obtained? This 0.15 upon 27 into 3/2 moles of hydrogen gas would be liberated. Okay, how much is that? Well, this is 9 to 18, 0.15 by 18, 15 by 18, that is 5 by 6, 0.05 by 6. Make sense? Makes sense. So many moles of, this is 1 upon 120 moles. 1 by 120 moles of hydrogen will be released. Fine. Now, they have asked me the volume. I know the moles, I know the temperature, I know the pressure, and V, I remember, is nRT upon P. How many moles? I have 1 upon 120 moles of hydrogen. R. Now, what volume? Volume is usually, if you report it in liter, R is 0.0821 liter atmosphere per mole Kelvin. This is how you should record it with units. Temperature, 20 degrees Celsius is 293 Kelvin. How did you do it? Temperature in Kelvin is temperature in degrees Celsius plus 273. I just add 273 plus 20, that makes it 293 Kelvin. Units of Kelvin cancel. Please never substitute in degrees Celsius, that is wrong. Divided by pressure. What is the pressure? 1 bar. I have this in atmosphere. 1 atmosphere is how many bars? Now, 1.013 bar is equal to 1 atmosphere. So, if you want, 1 bar is 1 upon 1.013. You could also use that, and roughly this is just 1 only. There's not much difference. Fine. What do? We calculate. How do we calculate? Let's see. This is 0.0821 into 293 into 1.013 divided by 120 liters. This is a calculation you need to make. Is it ugly? Whatever. It's not very pleasant, I must say. But once you do this, what do you get? You get the value as 0.2 liters or around 203 ml. This is the volume which you're going to obtain if you dissolve 0.15 grams of aluminium in excess NaOH as per this reaction. What will be the pressure exerted by a mixture of 3.2 grams of methane and 4.4 grams of carbon dioxide contained in a 9 decimeter cube flask at 27 degrees Celsius? How do we do this? It's a mixture of gases, right? So, we have mass of methane as 3.2 grams, mass of CO2 as 4.4 grams, volume is 9 decimeter cube, which is 9 liters because 1 decimeter cube is 1 liter, and temperature is 27 degrees Celsius, which corresponds to 300 Kelvin. Why? You add 273 in degrees Celsius and you get Kelvin. So at this temperature, this volume and these many moles, I'm supposed to find out the pressure. Now pressure of gas, a mixture of gases, is simply the sum of partial pressures also if you want. Actually what matters is just number of moles of gases. Identity of gases has no meaning. If I am given mass, well, what is molar mass of methane? Molar mass of methane is 16 and molar mass of CO2 is 44 grams per mole. So moles of methane is mass by molar mass, which is 3.2 grams by 16 grams per mole, which is 0.2 moles. And mass of CO2 is, which is how much? 4.4 upon 44, which is 0.1 moles. So you have mass of methane and mass of carbon dioxide. Lovely. Yes. So, I'm sorry, this is moles, not mass. These are moles. Perfect. Now, once you have moles, the total, N total is 0.2 plus 0.1, which is 0.3 moles. So I have 0.3 moles of gases. It doesn't matter what is the nature of those gas, methane, CO2, nobody cares. I have 0.3 moles of gas. And I'm supposed to find the pressure. Now P, the next step would be, P is nRT by V, which is 0.3 moles of gas into 0.0821 liter atmosphere per mole Kelvin into 300 Kelvin. That is the temperature divided by volume. And how much is volume? That is 9 liters. Liters cancel away. Moles cancel away. I would obtain the answer in atmospheres. How much is that? Now 300 into 0.3 will be 90. And 90 by 9 is 10. So that is simply 0.821 atmospheres. So the pressure exerted will be 0.821 atmospheres, and that would be all when it comes to mixture of these. In case you want to convert this, these are the values you get. That's fine. What would be the pressure of gaseous mixture, okay, when 0.5 liters of hydrogen? Now I must note down what is given. What is given is volume of hydrogen is 0.5 liters, pressure of hydrogen is 0.8 bar, and 2 liters volume of oxygen is 2 liters, and pressure of oxygen is 0.7 bar, are introduced in a 1 liter vessel at 27 degrees Celsius. Now, you have one sample and you have 2 samples, and now you are trying to mix them and introduce them in a 1 liter 300 Kelvin. Why? 27 degrees Celsius corresponds to 300 Kelvin. In this vessel, both these gases are filled, and I'm supposed to find the final pressure. How do I do that? Well, the way to do this is look at one gas at a time. Pressure finally is equal to partial pressure of hydrogen plus partial pressure of oxygen finally. So if I just find out what is the partial pressure of hydrogen and what is the partial pressure of oxygen in this vessel, I just add them and I get the final total pressure, right? How do I do that? Well, all I need to do is, when I have this much volume and this much pressure, temperature is not mentioned. And since nothing has been given, I am left with no option but to assume that temperature is constant throughout, otherwise the problem cannot be solved. So I'll just say that this is P1V1 is equal to P2V2 because temperature finally is same as initial, 27 degrees Celsius. So I can say that partial pressure of hydrogen into volume of hydrogen finally is pressure of hydrogen into volume of hydrogen initially. What was initially? I had volume of hydrogen 0.5 liters and pressure is 0.8 bar. And finally, I have 1 liter vessel. Volume of hydrogen is 1 liter into partial pressure of hydrogen, we don't know. Finally. So let us see. How much is this? Oh wow, this is 0.4 bar. So partial pressure of hydrogen finally is 0.4 bars. Is it fine? Yes. The same thing can be repeated for oxygen, and now in case you have not been able to do this question, half of it I have done, the remaining half you must stop here, do it on your own and then check. Oh, should you do that? You must do that. But nonetheless, I'm solving for oxygen also. Partial pressure of oxygen into volume of oxygen finally. Please note, there is nothing called as partial volume. Both the gases are occupying the complete vessel. So if the volume of vessel is 1 liter is the volume of hydrogen. At the same time, 1 liter only will be the volume of oxygen. Initially 0.7 bar and 2 liters. That means 1.4 bar. Partial pressure of O2 finally. The oxygen finally is 1.4 bars, hydrogen is 0.4 bars. So P total is 0.4 plus 1.4, which is 1.8 bar. That would be the final total pressure in the vessel. Density of a gas is found to be 4.56 grams per decimeter cube at 27 degrees Celsius and at 2 bar pressure. What will be its density at STP? Now, PM is equal to rho RT. Therefore, density is PM upon RT. Right? Now, If the same gas is changing temperature and pressure, please note molar mass of gas remains same. And molar mass and R is universal gas constant, it cannot change, right? So can I say that rho 1 by rho 2, what is rho 1? Density of gas under temperature pressure 1 by rho 2 is P1 by T1 into P2 by T2. Like this. If I just write it twice and divide them. How did you get this? I'll tell you, see. Rho 1 is P1 M upon RT1. Rho 2 is P2M by RT2. And what do? I divide. And from there I get this. Okay? This cancels and I get it. So all I need to do is, oh my God, substitute. Yes, it is 5.46 grams per centimeter cube. No, decimeter cube divided by rho 2 is P1. Density of gas is found at 2 bar and 27 degrees Celsius means 300 Kelvin. STP is 273 Kelvin and 1 bar pressure. Oh my God, that's it. That's it. So rho 2, solve this, is 5.46 into 300. Now 300 and 273 if you divide, you get 0.91. So this is 0.91 into 2. Kind of morbid. What it comes out to is so many grams per decimeter cube. This is 2.73 by 0.91. If you just see, it is 3 times. So this is 3 grams per decimeter cube. Very nice and neat calculations. So density at STP will be simply 3 grams per decimeter cube. 34.05 ml of phosphorus vapors. Oh my God. Let me note the data given. Don't even read the problem. Start noting the data. Volume is 34.05 ml of phosphorus vapors. Weigh, I'm given mass as 0.0625 grams. At temperature is 546 degrees Celsius and pressure is 0.1 bar. Really ugly, really dirty. What is the molar mass of phosphorus? Now, molar mass of phosphorus vapors. What they're asking is molar mass of phosphorus vapors. That is not very difficult to see. We have a pet equation. PV is nRT, which is m by m RT. Therefore, molar mass is mRT upon PV. All we need to do is to substitute mass 0.0625, 6.25 into 10 raised to minus 2 grams. R is 8.314, so many liter bar per mole Kelvin. You should know in different units. And temperature, we don't have space there, so we will use the spacing on this side. Temperature is really ugly, 546 and 273, 819 Kelvin. Kelvin cancels and whatever, divided by PV. How much is pressure? Pressure is given as 0.1 bar. The bar goes away with bar. And volume is 34.05 ml, means so many liters. Horrifying. Really ugly calculation. Jump around and do this. And grams per mole seems to be the very appropriate unit for molar mass. Just watch. If you want, I can just write it down in a slightly cleaner version. How much would that be? 819 into 6.25 into 8.314. Now 10 raised to minus 2 survives. kind of, and below we have 10 to minus 4 divided by 34.05, and this has to be multiplied by 100 into 100 grams per. This lovely calculation has to be performed. If you solve this, dears, you get molar mass as a very, very high heavy value as 1232.7 grams per mole, 1232.7 grams per mole. Now, is that not a bit too heavy? Yes, it is. Actually, one phosphorus atom is around 31 grams per mole. And phosphorus vapors are typically P4. And if they are P4, the mass should be 4 times 31, that is 124 around. So 123.27 would have been very nice. Yes, it is coming out to be 10 times. So this is the blessing of NCERT. If you just substitute, this is what you will get. Actually, in question, the pressure should have been 1 bar. Had the pressure been 1 bar, we would have obtained the actual pressure of the actual molar mass of phosphorus, which is 31.817 grams per mole for atom, and for molecule 123.27. But as per the question printed in NCERT, this is the answer. Which is okay, fine. Our exercise is done. Finally, the sensibility of it has to be ensured by NCERT, which they have failed to do, which is not very unusual. That's okay. Forget it. A student forgot to add the reaction mixture to the round bottom flask. Okay. So I have a round bottom flask at 27 degrees Celsius. But instead, she placed the flask on the flame. Okay. After a lapse of time, he realized his mistake, and using a pyrometer, he found the temperature was so much. Now, apparently, this round bottom flask was there. Initially, it was this much, and finally, the stupid flask has been heated to 477 degrees Celsius. There is some flame here, etc. What fraction of air would have been expelled out? Now, it is an open flask. So as you heat it, air from it ejects out. Yes. Do you note that what is the volume of air in the flask? How do I count that? I just imagine that, see, this is kind of the boundary, and whatever are the number of moles of air contained in it, that is the air contained in the flask. Since it is open to atmosphere, and are you aware that whenever you're talking about atmosphere, atmosphere is always at a constant pressure of 1 atmosphere unless mentioned otherwise, right? So for both these flasks, volume is constant. Pressure is 1 atmosphere, which is constant. Why? Because since it is open to air. Oh my God. What is changing? What is changing is number of moles. Initially, I had some N1 moles of air and temperature was T1. Now, certain number of moles have ejected. So now I have N2 moles of air and temperature is T2. Right? Fine. Can I find relation between N1, T1, N2, T2? I can. Why? See, PV is equal to nRT. Now pressure is same, volume is same. So I can say N1 T1 is equal to N2 T2. So moles initially by moles final is temperature final by temperature initial, and final temperature is 477 degrees Celsius. 477 and 273, if you add, you get 750 Kelvin. So final temperature is 750 Kelvin. Initial temperature 27 degrees Celsius is 300 Kelvin. How much is this ratio? This comes out to be 2.5. So initial and final moles, the ratio is 2.5. And what they have asked you is what fraction of air would have been expelled out. So you can say fraction of air expelled. Can you find the expression for it? Yes, this is moles of air expelled by moles of air initially. Whatever is expelled divided by whatever was with the initially, that is fraction expelled. Now what is there initially? Ni. I stands for initial. So denominator is clear. Initially it was Ni. Finally it is Nf. So what is expelled? Whatever was there minus what has been, what remains. See, how did I get this? I repeat, initially I had some number of moles. Finally, I am left with some number of moles. The difference is nothing but the number of moles of air expelled. Otherwise, why will final be different from initial? Final is different from initial because some moles have been thrown away. Yes, good. I have a relation. Of course, I have a relation. N final is 2.5 times, no, so 2.5 times N final is N initial. So N initial is 2.5 N final minus N final upon 2.5 N final. Oh my God, this is cancelling, yes. And this comes out to be 1.5 by 2.5, which is 0.6. Fraction of air that has been expelled out is 0.6. Or if you want to convert this to a fraction, 3 by 5. 3/5 of the original air has been expelled because of this heating. Calculate the temperature. Wow. I must note the data. So temperature has to be calculated of 4 moles of a gas occupying 5 decimeter cube at 3.32 bar. I just have to substitute in PV is equal to nRT. T is PV by nR. How much is pressure? Pressure is 3.32 bars. And volume is 5 decimeter cube. Moles is 4 moles. And R is 0.083 bar decimeter cube per mole Kelvin. Bar and decimeter cube cancel away, mole cancels away. You must substitute with units so that you don't go wrong in such questions. How much does this come out to be? Well, 3.32 into 5 divided by 4 into 0.083 Kelvin. What I need to do? Of course, I need to do the calculations. I calculate. And once I calculate, very neatly, the temperature comes out to be 50 Kelvin. 50, it's a nice, lovely round figure if you care to note. Yes, it comes out to be 50 Kelvin. Calculate the total number of electrons present in 1.4 grams of dinitrogen gas. Well, doesn't sound very awful. I have 1.4 grams of dinitrogen. That means 1.4 grams divided by 28 grams per mole. How much is this? Which is 1 upon 20 moles of N2. Now, one nitrogen atom contains 7 electrons. So, N2 molecule contains 7 into 2, which is 14 electrons. So, it must contain just barely 14 electrons. Yes. So, N2 molecule contains 14 electrons. Yes, that's fine. What goes next? One molecule contains 14 electrons. So many moles, therefore, moles of electrons is by 1 by 20 moles into 14, which is 0.7 mole electrons, which is 0.7. I just multiply. So many electrons. What does that come out to be? It comes out to be these many electrons, 4.2154 into 10 raised to 23 electrons. How much time would it take to distribute 1 Avogadro number of wheat grains? If 10 raised to 10 grains are distributed every second, 10 raised to 10, that means 10 billion grains are distributed every second. Fine. You have Avogadro's number of wheat grains. So, number of seconds is 6.022 into 10 is to 23 grains divided by 10 is to 10 grains per second, which is 6.022 into 10 is to 13 seconds. This is the time, my dear, you would need. Is it fair to leave this in seconds? Let's convert it to at least years, right? 6.022 into 10 is to 13 seconds. That means divide by 60, so many minutes, divided by 60, so many hours, 24, so many years, so many days, into 365. Normally, if you avoid leap years, otherwise you should take 0.25, so many years. So many years would be required. How much does that come out to be? Well, that comes out to be 1.9 million years. So, when dinosaurs were roaming around the earth, you start distributing only one Avogadro's number of wheat grains, and you distribute 1 billion grains every second, and you go on and on and on. Still, you would need 1.9 million years to distribute that much wheat. It is an enormous amount of wheat, obviously. Calculate the total pressure in a mixture of 8 grams of dioxygen. Let's note the data. What is given? What I'm given is mass of dioxygen is 8 grams and mass of dihydrogen is 4 grams. Confined in a vessel of volume is 1 liter. 1 decimeter cube is same as 1 liter. Don't get confused. Temperature is 27 degrees Celsius, which is 300 Kelvin. Why? Add 273 and get in Kelvin. R I have been given, and I am supposed to find the final pressure. Now, total pressure is same as sum of partial pressures. We are aware of that. Can I find out partial pressures? Yes. I am given masses. Can I not calculate moles? Fine. Now, molar mass of oxygen is 32 and hydrogen is 2 grams per mole. And number of moles is mass by molar mass. 8 by 32, which is 1 by 4 mole, and 4 by 2, which is 2 moles. So, I have N total as 2.25 moles. If I just add those 2 moles, I get 2.25 moles. Can I add moles? Of course I can. And how much is pressure? Pressure P. The next step, I'll change the ink. Pressure P is nRT by V. 2.25 moles. How much is R? 0.083 bar decimeter cube per mole Kelvin into 300 Kelvin divided by volume. How much is volume? 1 decimeter cube. Fascinating. The ugliness itself is fascinating, but not very ugly, no big division, just one multiplication. You multiply and what we get is 56 bars. Roughly 56 bars of total pressure would be there. Payload is defined as the difference between the mass of displaced air and the mass of balloon. What is all this nonsense? Actually, what they are referring to is a hot air balloon, or in general a balloon. If you have a balloon like this, fine. And if you are trying to hang a bucket, if you are trying to ride the bucket and go up in the air with the balloon, they are trying to give you some idea about payload. We will talk about that. What is payload? See, when a balloon is floating up in the air, any spaceship, any aeroplane, whatever, they have a mass of their own, right? So a balloon must fly itself. A balloon has a mass of its own, indeed. Whatever extra weight it can carry, that is called payload. I mean, one thing is, I'm carrying, see, if I climb, say, a mountain, I'm climbing myself. That's fine. I have to carry my own weight. If I'm carrying some extra weight, then that extra weight will be called the payload. They are giving you some kind of a feel, how can you calculate payload? We can do that. We don't need the gyan. Let's read the other part. Calculate the payload when a balloon of radius 10 meter. Now, we have radius of balloon is 10 meters. So it seems like a spherical balloon. Mass of balloon is 100 kg. Quite tremendous. Is filled with helium. Now this is helium. Pressure is 1.66 bar. Temperature is 27 degrees Celsius. That is 300 Kelvin. Density of air I am given is 1.2 kg per meter cube. Fine. Now, in general, if a balloon is just able to float, can I do a simple force balance? Yes. And what would that force balance say? That upward force is the buoyant force and the downward force is mg. And a limiting case, upward force has to be equal to downward force. Now, what is pulling down? Mass of balloon plus mass of helium plus payload. This is the mass which is pointing into gravity. This was pointing downwards. What is upward? I recall Archimedes' principle. It says that whenever a substance is immersed in a fluid completely or partially, it experiences an upward force, and the force is equal to, magnitude of force is equal to what? It is equal to the mass of fluid displaced by the immersed part of the body. So this is equal to mass of air displaced. All this must be equal to this, right? And mass of air displaced must be equal to density of air into volume of air displaced. But how much of air has been displaced? Same as volume of balloon. Density of air into volume of balloon. Let us say payload is some number P. How much is mass of helium? Mass is moles multiplied by molar mass. Moles of helium into molar mass of helium, which is 4. Mass of balloon is given to me. Of course, force is this much into gravity. Gravity will cancel away. So we don't need that in next step. Plus mass of balloon. Mass of balloon plus payload. They stay where they are. N is PV by RT. This is pressure of helium into volume of helium by RT into molar mass of helium. This is so much. Can I calculate payload? Yeah. Payload P will be equal to all this dirt. Now volume of helium and volume of balloon are the same. So volume of balloon becomes common. This is density of air minus all this goes on that side. What is this? Pressure of helium into molar mass of helium by RT. Actually, this is nothing but density of helium. Fine. Minus mass of balloon. I have got a formula for payload, right? Difference between the mass of, this is mass of displaced air and mass of balloon, right? Can I substitute? Well, this is all I can do, so let us do that. How much would that be? Let's calculate. Volume of balloon, which is 4 by 3 pi r cube, to payload will be 4 by 3 pi r cube. R is radius, which is 10 meter. This will be volume in meter cube, please remember. Now, if you want to convert this to decimeter, please remember 1 meter is equal to 10 decimeter. So, if you are interested in changing units, one could also change this unit. Instead of 10 meter, I can write how many decimeters? I can write 100 decimeters. This becomes easier. So this is volume of balloon. What do I have? I have density of air, which is 1.2 kg per meter cube, minus this thing. So I have 1.2 kg per meter cube. No, this is dangerous because units are in meter cube here. Never mind. Minus the helium stuff. What is that? Molar mass of helium is 4 grams per mole. Pressure of helium is 1.66 bar. Divided by RT, R is 0.083 bar decimeter cube per mole Kelvin into temperature is 300 Kelvin. Minus mass of balloon, which is 100 kg. Let it continue. Let's watch the fun. First of all, be careful about the units because this seems to be having mixed units. Bar cancels away with bar, mole with mole, Kelvin with Kelvin. So I'm going to obtain something in grams per decimeter cube here, it looks like. This is 1.2 kg per meter cube. Fine. Minus 1.66 into 4 upon 0.083 into 300 grams per decimeter cube. Now 1 gram is 10 to the minus 3 kg, or decimeter cube is 10 to the minus 3 meter cube. So grams per decimeter cube is same as kg per meter cube. There is no difference. So they have same units. All I need to do is to multiply this and calculate this. तो आपको बस इसी को आगे solve करना है. 4/3 pi 22/7 into decimeter की जरूरत नहीं है, kg per meter cube में काम चलाएंगे, बढ़िया है ना. तो 10 meters इस पूरी 4/3 pi r cube, ये इतना ही है ना, ऐसा. ठीक, तो ये आ गया वॉल्यूम मीटर क्यूब में. ग्राम्स पर डेसीमीटर क्यूब को हम केजी पर मीटर क्यूब भी लिख सकते हैं मजे से. -100 kg ऐसा आ जाता है. यूनिट्स बड़ी कंसिस्टेंट है. मीटर क्यूब यहाँ पे कट जाएगा. ये आ जाएगा मास ऑफ एयर डिस्प्लेस्ड इन किलोग्राम्स -100 kg. ये आ गया पेलोड. अच्छा खासा पेलोड है 3811 kg. इतना सामान लाद सकते हैं जो बलून ढो के ऊपर ले जाएगा, अगर आप ये सब करने में समर्थ हैं तो. Calculate the volume occupied by 8.8 grams of CO2. Given लिखना मत भूलिए. Given क्या है? Mass of CO2 is 8.8 grams. Temperature is 31.1 degrees Celsius. Pressure is 1 bar. और वॉल्यूम पूछा है कितना होगा, हाई. कैसे निकालेंगे ये? अब PV is equal to nRT, direct substitution. V is nRT upon P. Moles, how many moles do you have? 8.8 grams. Now moles of CO2 is mass of CO2 by molar mass of CO2, which is 8.8 upon 44, which is 0.2 moles. So I have 0.2 moles into R, 0.083 bar liter per mole Kelvin into temperature. How much is temperature? Temperature is 31.1 degrees Celsius plus 273, 304.1 Kelvin. This is, and by pressure P, how much is pressure? 1 bar. The simple, nice, sweet, happy multiplication has to be done. And once you do that, you get the volume which is occupied is 5.05 liters. That would be the volume of CO2. 2.9 grams. Please note down the data. Mass of gas is how much? 2.9 grams of a gas at 95 degrees Celsius. 95 and 273, if you add 368 Kelvin, horrifying, occupies the same volume. Okay, it has some volume V0, and there is another gas. We have mass of hydrogen as 0.184 grams. Volume is V0, temperature is 17 degrees Celsius, which is 290 Kelvin. At same pressure, pressure is same, volume is same. What is the molar mass of gas? Now, PV is equal to nRT. So, very conveniently I can say that N1T1 is equal to N2T2, right? Instead of moles, I have molar mass. So, M1 upon capital M1 T1 is M2 upon capital M2 T2. What do? We substitute. That's it. And how much is that? Let's do that and see. Mass. How much is mass? Mass is 2.9 grams. By molar mass, we have to find out. Temperature was some dirty temperature. That was 368 Kelvin. Is 0.184 grams of hydrogen. Molar mass of hydrogen is 2 and temperature is 290. That's it. So, M1 comes out to be 2.9 by 0.184 into 368 upon 290 into 2 grams per mole. Fascinating though it may sound, ultimately it comes out to be very round figure of 40 grams per mole. The gas looks like argon. A mixture of dihydrogen and dioxygen. Now I am given a mixture, so let me sketch a mixture also. I have H2 and I have O2 at 1 bar pressure. Now 1 bar is pressure of what? That is the total pressure actually. It contains 20% by weight dihydrogen. Now pressure is P total is 1 bar. Fine. And am I given something? And let's say total mass is M0. Then it has 0.2 M0 and 0.8 M0. Fine. Calculate the partial pressure of dihydrogen. Masses are so many. What are molar masses? Molar mass. Hydrogen is 2 grams per mole. This is 32 grams per mole. So, can I calculate number of moles, which is mass by molar mass? Mass 0.2 M0 by 2. This is 0.8 M0 by 32. These, my dears, are the masses and the number of moles of dihydrogen and dioxygen. How much does this come out to be? This is 0.1 M0 and this comes out to be 0.1 upon 4 M0. Okay. So, if you just see, these are number of moles. So, N total is 0.5 upon 4 M0. If I just add them, I get this much. Can I find mole fraction? Of course I can. How would I do that? Now, mole fraction of hydrogen is moles of hydrogen by total moles, 0.1 upon 0.5 by 4, which happens to be 4 by 5, which is 0.8. So, mole fraction of hydrogen is 0.8, right? And partial pressure of hydrogen is mole fraction of hydrogen into P total, which is 0.8 into 1 bar, which is 0.8 bar. So, hydrogen amounts to 80% of the total pressure, although its mass is barely 20% because number of moles of hydrogen are more. What would be the SI unit for the quantity P V square T square by N? How do we do this? Just substitute. we have P, V square, T square by N. What is the SI unit for pressure? Pressure is bar. So this is bar. V square. Now, what is volume? Volume is in meter cube. So meter cube square. Temperature is Kelvin square. By N is mole. No square. Nothing. That's it. Is it good enough? Kind of. You could say this now. Bar, if you want, you can translate. Bar is Newton per meter square. So, in pascals, if you take pressure, that again would be newtons per meter square. A little cleaner than this. So, you could say Newton per meter square here. Still, what would that come out to be? This is newtons meter to the power 4 Kelvin square by mole. Newtons also you can open up. Force is in newtons, which is mass into acceleration, which is kg meters per second square into meters to the power 4 Kelvin square by mole. If you simplify further, you have kilograms meter to the power 5 Kelvin square by second square into moles. These will be the ultimate simplified fundamental SI units for this expression. In terms of Charles' law, explain why minus 273 degrees Celsius is the lowest possible temperature. Now, what is Charles' law? What did Mr. Charles do? Charles' law says that if you take a fixed amount of gas, that means fixed number of moles of gas at constant pressure, and you measure its volume at different temperatures, right? Then you would find that volume of any gas is proportional to its absolute temperature T. Volume of any gas is proportional to its absolute temperature T. So V1 by V0 is T1 by T0, something like this. Now, what is V1, V0? V0 and T0 are some initial temperatures and volume. V1, T1 are final volume and final temperature, or at any other condition as such. Can we plot this graphically? Yes, we can. And instead of absolute temperature T1, this is T1 degrees Celsius plus 273, you could also take like this. Very interesting. If you plot this graphically, you get very interesting points like this. You would discover that whenever volume versus temperature is being measured, and if you plot all of these graphs, you would discover that first of all, these are lines of fixed slope. They will be obtained, very beautiful, like this. And all these lines converge at a single point. And what is this point? This is minus 273.15. Yeah, if you neglect this 0.15, normally people just approximate this, minus 273 degrees Celsius. That's it. Since at minus 273 degrees Celsius, all these lines converge, and if you just want to go below this, volume will become negative. Now, and volume cannot become negative. Volume, the lowest volume possible would be 0. You can't get negative volume. So, by Charles' law, you can say that minus 273 degrees Celsius is the lowest possible temperature. Since below this temperature, if that is possible, the volume would become negative, which is impossible. So, that is the lowest possible temperature. Critical temperatures for CO2 and methane are 31.1 degrees Celsius and minus 81.9 degrees Celsius respectively. Okay. Which of these has stronger intermolecular forces and why? Critical temperature, my dear, depends upon the intermolecular forces of attraction. Higher the intermolecular forces of attraction, higher is the critical temperature. And since critical temperature of carbon dioxide is much more than methane, it means that carbon dioxide has much higher intermolecular forces as compared to methane. Now people are asking why. This is the simplest reason I have given you. But if you want to go down by one more deep level, I can also tell you this by definition of critical conditions. What is critical temperature? The highest temperature beyond which a gas cannot be liquefied by applying any amount of pressure. That means that if you apply any amount of pressure to CO2 which is more than 31.1 degrees Celsius, there is no way you can condense CO2 gas to a liquid or solid. It will always stay in gaseous state. Okay. So what does it mean? It means that if I take temperatures below 31.1, if I apply pressure, CO2 can become liquid or solid? Yes. Why does a gas become liquid or solid? It becomes liquid or solid because it has intermolecular forces of attraction. At higher temperatures also, if it can become liquid, that means it has greater attraction. Because if you increase the temperature, the tendency to become vapor increases. And if it is not becoming vapor, if it is staying as liquid or solid, it means that it has greater intermolecular forces of attraction. Simple logic. So, greater the intermolecular forces of attraction, higher is the critical point. Hence, much more intermolecular forces of attraction exist in carbon dioxide as compared to methane by looking at critical point. Explain the physical significance of van der Waals parameters. There are two van der Waals parameters, small a and small b. Let me write down van der Waals equation also. It is P plus A by V bar square. V bar minus B is equal to RT, where V bar is molar volume V by N. You have more dirty form also, but this is the simplest form. Now, A and B are called van der Waals parameters. And A represents intermolecular forces of attraction. Higher the intermolecular forces of attraction, higher is the value of A. For example, in water vapor, attraction is much more because of hydrogen bonding. So A for water vapor will be much higher as compared to, say, helium, which has negligible intermolecular forces of attraction. B represents actual volume occupied by gas molecules. So if the actual volume of molecule is bigger, P is bigger. So if you have a bigger molecule like, say, benzene, benzene would have a larger value of B as compared to a smaller molecule, say, for example, argon or helium for that matter. So if you have smaller atoms or molecules, you have smaller value of B. If the size becomes bigger, value of P becomes bigger. How do you distinguish? Also, like say if you have something like hexane. Now hexane is a huge molecule, C6H14. So B for hexane will be very large. But because hexane is non-polar, you would find intermolecular forces of attraction, or A for hexane, may not be equally high or very high as compared to, say, if you take some other gas like chlorine. Now chlorine is a small molecule. So, but then it may have a higher intermolecular forces of attraction. This, my dears, was discussion of NCERT States of Matter, Unit 5 of Standard 11th. I am Shishir Mittal from Vyas Certification. For more knowledge, for more help, do download our app and connect with us. All the best.